This is the video for 2.2 polynomial functions. A polynomial is an expression that is a result of the sum of monomial terms or functions. So first we're going to look at the leading term test. It uses the power and coefficients to determine the polynomial end behavior. So your leading coefficient is going to be your number that's in front of your highest degree. This is your leading coefficient. This n would be your highest degree. So the number that's in front of your highest degree is your leading coefficient. So your right end behavior should match the sign of your leading coefficient. So if it's positive, it points up on the right. If it's negative, it points down on the right. The highest degree helps determine how many maximum or minimums, basically kind of how many humps your graph has in it. So your number of turning points, the number of maximum turning points, is going to be whatever your highest degree is minus 1. So we already know what a quadratic looks like, which is an x squared, and as you can see, you only have one turning point, whether it's up or down, but you just have one place that you're changing direction from increasing to decreasing. Same thing with x cubed. I'm going to exaggerate the x cubed graph. So you have two places where it's changing from increasing to decreasing. And same thing if you go the other way, you still have two turning points. If I have an x to the fourth graph, and it's not just a plain x to the fourth, it could be x to the fourth plus 2x cubed, whatever it is. You have 3 turning points. So there's one less turning point than there is degree. So let's take a look at a couple of examples. So for example 1, we have f of x equals x to the fourth plus 2x cubed plus 3x minus 1. I want to know how many turning points. So in order for me to know how many turning points, we're going to have to look at my highest degree, which is that 4 up here. Let me change this to an arrow. Okay, so we're going to be looking at this highest degree up here, which is 4. And so your number of turning points is going to be 4 minus 1, the highest degree minus 1. So there's 3 turning points. On a graph, whatever the sign of this leading coefficient is, in this case is positive, that means your graph is going to point up on the right. And if I have 3 turning points, we're going to continue. So there's 1, 2, 3 turning points. As you can see, it's pointing up on the right. This matches, let me just do my finger, the sign of your leading coefficient. And there's 1, 2, 3 turning points. So right now, before we get into exact zeros, when I ask you to sketch a graph based on this information, that's exactly what it wants you to do. So your end behavior in this case is your limit as x approaches infinity of your function. On the right hand side is positive. Your limit of your function as x approaches negative infinity, you can see equals positive infinity also. And then there's your sketch. I kind of did the sketch first, and then it's easier to do the end behavior from that afterwards. And in a second, you will kind of see when it's even, they're both going to be up or both are going to be down. If it's odd, they're going to go in opposite directions. Okay, next one. F of x equals negative 5x cubed plus 3x squared minus 2x plus 3. How many turning points? So my highest degree right now is 3. So my number of turning points is going to be 3 minus 1. So there's going to be 2 turning points. So my end behavior, and without graphing it, I'll kind of do this. So I'm going to look at my leading coefficient. Since this is negative, that means my graph is going to point down on the right. Well, here, actually, I'll do it down here. It's going to point down on the right. If I have 2 turning points, then I'm going to just finish the graph. 1, 2. On the left, it's going to end up going up like this. So my end behavior, if I write it out in limit notation, my limit as x approaches infinity That's the right side one. Goes to infinity. And my left side one, I'll do it over here. My limit as x approaches negative infinity, which is this left-hand side of my function, is positive infinity. You can see down here that I have two maximum minimums. I'm pointing down on the right, which matches this sign right here, my negative sign. Okay, example 3, x to the 5th minus 2x squared. My number of turning points is going to be 1 less than my degree of 5. So there's going to be 4 turning points. Then my end behavior, I need to figure out my coefficient is 1, and since that's positive, that means I'm going to go up on the right, and since this is an odd number of 5, that means my end behaviors are going to go in opposite directions. When it's an odd number, they go in opposite directions. Just think odd, opposite. When it's even, they'll go in the same direction. So it goes down on the left. So I'm going to sketch a graph, and then I'll go back and do end behavior. So on the right, it's going up. I have 4 turning points. So I'm going to come down here and finish my graph with 1, 2, 3. 1, 2, 3, 4 turning points. So here's 1 turning point, 2, 3, 4. It's pointing up on the right, which matches the sign of my leading coefficient, which is a positive 1. And so for my end behavior, this is my right end behavior, my limit as x approaches infinity of f of x, it's pointing up, so it's going towards positive infinity. And on the bottom, my left end behavior, my limit as x approaches negative infinity of f of x is negative infinity. Okay, now we're going to get a little more accurate on our graphs, and we're going to find some zeros so that we can graph more accurately. So for example, on example 4, I have f of x equals x cubed minus 5x squared plus 6x. So when I want to find some zeros, when I ask you to find some zeros, you're probably going to have to do some factoring to get it. So let's look at my graph. I can take an x out of each term. So I have f of x equals x parentheses x squared minus 5x plus 6. I still need to factor this equation right here. I need to figure out what multiplies to be 6, adds to be negative 5. So that's going to be x times, split up my x, I want a 3 and a 2, and a minus sign. So now each one of these, my x minus 3 and my x minus 2, I'm going to set equal to 0. And I'm going to get my zeros. So I'm going to get x equals 0, x equals 3, x equals 2. So those are the places that my graph is going to cross my x-axis. So I'm just going to kind of draw them on here. So I have 1, 0 at 0. I have 1 at 3. And I have 1 at 2. And I notice from my graph that this is an x cubed graph, so that means I'm going to have 2 turning points. And since this is a positive 1, I'm going to start up on the right. And as long as there's only one of each, meaning that there's no squares up here, you're basically just going to go through the graph like it's a line. And that is going to be my basic sketch of my graph. So as long as there's only an exponent of 1 on each one, you're going to go straight through, okay? If there's squares on these, we're going to talk about that in a minute when we talk about multiplicity. Instead of going through the graph, you might basically bounce off, or you might go through it so that it looks like a cubic. I'm going to talk about multiplicity on the next screen. Okay, sometimes we have more than one of the same term. We refer to this as multiplicity. And all it means is that the graph looks a certain way when it goes through the x-axis. So if we look at a leading coefficient of 1, that basically means the degree of that particular term in your factor, that means you have a multiplicity of 1. So when you're on the x-axis, you're basically going to go through it, whether you're going to go through it with a positive looking slope or whether you're going to go through with a negative looking slope if you have a degree of 1. If you have a degree of 2, when you approach the x-axis, you're going to do it like a quadratic, which means you're going to bounce off if you have a degree of 2 when you approach it. So a degree of 2 up here basically means that you're going to hit the x-axis and bounce off. So that at that particular 0, it looks like a quadratic. Down here, it looks like a quadratic. So an x-cubed graph, if you remember, it looks like you're going through kind of like a snake. So on the x-axis, when you go through it on the x-axis, let's put one here. You're going to go through it. It should look like an x-cubed graph at that particular point. So when you put a whole bunch of these together with different factors, it's going to look like you're sandwiching lines and quadratics and cubics just in a certain fashion.